How's everybody doing? How's it going with assignment 4? Yep. Yep. Yeah, so you need to know the size of every subtree, and the larger one should go on the left. And the larger one goes below, is that correct? Yeah. The smaller one goes below, the larger one goes above. The easiest thing to do is to know the size of every subtree, and one way to keep track of that is to have a hash map from the tree nodes to their size. Well, that's not true. The easiest thing to do is just call the size function every time you know the size of the node. That's too inefficient because the size function traverses the whole tree to the size. So that means that if you do this, eventually you'll do this at every node. There'll be subtrees that you're traversing over and over and over again. You just get the size of that node, you traverse the subtree, and the parent, you traverse the subtree, and so on. So with one pass through this thing, you can compute the size of every node that's stored. No, you can't. So the question is, just knowing the size of the subtree below you, do you know how far you should go to place the child to the right? The answer is no. The size doesn't tell you that because it all depends on the left or right and how that tree is built. So instead, what you do is you first draw the stuff below you. That draws it, and you can return a value like what's the largest, the max x coordinate, and you use that value. And actually, so there's a place where recursion cannot hurt. And that's because that subtree is the smaller of the two subtrees. Right? The one below is the smaller of the two. So if you recurse on that subtree, you're recursing on something that's only half the size. So if you only recurse on the smaller subtree, your recursion depth is only log n. It's not going to be linear. That's the place where recursion will actually stay.
What is recursion? That's error. Sort of like a null pointer exception, except the draw it well.
But that could be just, it draws it well on your screen, but gives you a null pointer exception on the server. That just means the server is dealing with some kind of tree that you haven't tried on your it's not because of it. So I have a couple of questions for you guys. So you know this course is weighted, 50% of the course is weighted to the assignments and 50% is weighted to the exams. Now that for me is what is actually not the way I like it. I'd like it to be almost 100% assignments because I think the assignments are the most worth it for us. And the exams are just there to check that indeed you did understand what you did on the assignments and not that you somehow did well on the assignments without understanding. So it's not going to change for you guys, but maybe future people. So what do you think of that grade distribution? Is that a fair weighting of grades? Yep. Okay, so even heavier on assignments. Yeah. Anyone else feel that that's fair? I mean, the bulk of the work in this course, the main station we have assignments. Exams are something you prepare for, like 2 days in advance and then break. Okay.
What about a weighting scheme?
I'm a little concerned with that. and it's for the same reason I'm a little concerned about the 75%. So, you know, the submission server, we do some checks to look for things like duplicate assignments and stuff, but it's not too much work for somebody to take an assignment, someone else's assignment, and change it enough that we couldn't tell that they're duplicates. And so that leaves open the door for people to really get through the course without understanding anything. And I don't want that. Yeah?
Could it be like a heavier weighted assignments, but you have to pass the exam?
That is an option. So there are classes where assignments are heavily weighted. Well, none of the assignments are heavily weighted, but there's a rule that you have to pass the final exam to pass the course. So it doesn't matter how well you do in the semester, you don't pass the final exam, you don't pass. It's a little, it seems like a lot of pressure to put on someone on a one-day event, 2 hours of your life, 25 days, and your whole semester is wasted. So I'm a little leery about that, but that would solve the problem. Would solve the problem of people getting through the assignments another way. But you don't think that the assignments are weighted too heavily? So people don't want exams that are weighted more. Okay, good. Because I do occasionally get requests for that. Because I get requests for everything, right? So anybody who's doing better on exams than assignments says, can you weight the exams more heavily? And anybody who's doing better on assignments says, can you weight the assignments more heavily? So something like this, if we could find a better way to deal with the possibility of people borrowing ideas from others, detecting that a bit better, we can go more heavily on the assignments. So next question for you guys is, we're thinking of putting together an online version of this course. It would be the same structure, except that the lectures would be replaced with video tutorials. So you go and you watch. They'd be kind of different from what happens in class. They're sort of PowerPoint slides, but they'd be very short things, a couple of minutes each, followed by a little exercise related to this. So, you know, when I do something like explain, I don't know, an array list was one of the first non-trivial things we did. You know, one exercise would show you, or one lesson would show you how you add an element, how you remove an element, and how you get set elements. And then another exercise, or another lesson will show you the resizing and maybe the analysis of resizing, each one with a sort of exercise afterwards. So if you had the option this year to take the in-class course or the online course, which would you prefer, or would you just like to have both? So who would like to take the online course? So even among the people who are coming to class, there's a fraction of you who are interested in that. And I can assume that the people who are not coming to class would be more interested in the online class. Yeah, so the nice thing about that is we intend to offer it both ways, which means that the people who are coming to class also have the benefit of all the online materials. So, you don't have to choose, but I just want to know if there's any point. Seems there is some interest. Okay, good. Any questions before we start the real lecture?
Yeah, so if you did the online little assignments, that might take the weight off the assignments as an extra little thing to it.
Well, so they would be not, I think that the exercises are just really there to stimulate, to avoid something like a course a lecture that becomes watching a 1 hour long video, which I think is terrible. First of all, it's really hard to watch a video for an hour. It's hard enough to watch someone stand up and lecture for an hour, but a video is bad. But it's also completely non-interactive. So the point is to simulate something like I do the talk for a few minutes, and then I ask you guys a question. And somebody should answer it before we proceed. And that's why the videos would only be a few minutes long, just with a very small part of a very specific topic. And some benefits of that are, well, in a class this size, the number of people who usually answer questions is only a small number of you, and there's just, even if that other people did want to answer questions, there's just not enough time to have 250 people all answer. So the nice thing about an online course is everybody gets to participate, and everybody gets to take as long as they need to figure out how to answer a question. Not too fast or too slow, hopefully, for anyone. Yeah, but that might also affect the structure of the assignments, where they would be smaller assignments than more frequent. I don't know what to make of that. Yeah.
I think that also could work with, even if you put like almost little sort of tutorials into it, so that kind of takes you off of other things too, and it helps you more frequency every day.
Yeah, so we could do some quiz type things as well. So you watch the lectures on array lists, do the exercises that you watch, and then at the end, when you feel you're ready, you can take a quiz. And it's sort of like the tutorials that you get at first year. You get some smallish target mark from doing those things. And hopefully that just prepares you for exams as well. Yeah.
If you think about the class, like the actual class lectures, is that similar to my class lectures, someone else at the same time?
Yeah.
Online, the online class, there's much more chance of asking questions.
Yeah. So don't get me wrong. I don't think that online courses are better. I think that it's great to have a class where you can stop the instructor and ask for clarification. So the hope is if that kind of thing happens, then that's what course forums and things are for. So, I didn't understand this part of the video, why did this happen? You ask that on the course forum and 10 other people reply, and maybe there's a more formal record of that so that someone who's been maintaining this course can go back and improve that section of the videos to make that more clear. Whereas now, when people ask me the same questions year after year in class, I forget immediately, and I teach exactly the same way the next year, and people ask the same questions. So it's nice to have a more formal record if someone is going to really take care of the online materials. We'll see. Okay. Anything else? Good. So today we're going to start looking at sets. We've seen it all: amortized data structures, randomized data structures, and worst-case data structures. Now we'll look at priority queues, which are simpler than sorted sets. Basically, anytime you have a sorted set, you can usually turn it into a priority queue very easily. And remember, we talked about this very early on. It's important. Queue operations. You can add an element to a priority queue. You can remove, but you don't get to say what gets removed. And this also has the name delete in other text. This is remove the smallest value from the priority. So it's a remove that takes no argument. You don't get to choose what gets removed. It's the smallest value that gets removed. And related to that, although it's not strictly necessary, is find min, which is return the smallest value in the priority. So these are the three basic operations of a priority queue. Sometimes you split these two because you can do this one faster than this one. But find min is not strictly necessary because you could you always remove something, that gives you the minimum value, and then just add it back in if you didn't really need to take it out. Okay. And so what are these things good for? Well, I can tell you two applications now, and then we'll see another application once we do an algorithm. So what are they good for? Well, here's one thing that they're good for is sorting. So if I want to sort a list of n numbers, I can create a priority queue, add each number to that priority queue, and then I'll remove n times, and the numbers will come out of the queue in sorted order. First the smallest one, then the next smallest one, the third smallest one, and so on. So you can sort n elements by n add x operations, followed by n remove operations. So that's one application. And we'll see when we do sorting algorithms, one of the best sorting algorithms known is exactly that. You build a priority queue and you remove all the elements. So, turns out you can do that in a very nice, compact, efficient way. Another such thing is what's called discrete event simulation. And we'll see an algorithm that uses this idea. But think of things like games or simulations, where there's a lot of different agents, different actors in the game that are all have things that they want to do. It's deletion. These two things are the same thing. It's just that every textbook in the world calls it delete min, except Java calls it remove. But the same thing. So I mean, here's the simplest example. You have a pool table. You're implementing simulating a pool game, or maybe it's particle interactions or something. And what you know is that you start out and this particle is traveling in this direction at some velocity. So when this happens, you realize that at some point in time, this thing will collide with this other particle. Okay, so at some time t, this is going to happen. So you now have a priority queue in which you put the event of this collision happening with the timestamp t. So this is going to happen at time t. And now you look at the priority queue and say, okay, what's going to happen next? Well, that's the event with the smallest timestamp. That's the soonest event that's going to happen. And so you remove this thing from the queue, which is like fast forwarding this picture to the point where this ball has moved all the way to there. So you're simulating a continuous process where the ball is really moving continuously, but nothing interesting happens between the ball moving here and the ball moving there, so you just fast forward to that thing. And now this collision happens, and that does a couple of things. It pushes this ball in this direction, and this ball moves on in this direction. And now each of these gets two events. At some point, this ball gets its event. At some point, this ball is going to collide with the wall, and this will be time t1. And at some point, this one is going to collide with this thing at time t2. And so you remove this event. Now you've got t1 and t2 in your priority queue, and now you remove the minimum to advance to the next state. And so you can have hundreds of these things or thousands of these things. Each one is going to have some event that happens next, and what you're interested in doing is fast forwarding to the time where the next event happens. And in this way, you get a perfect simulation. The alternative is to do something like, well, you guys, many of you took comp2402 with me last year, where we did games in Pygame. The alternative is to do something like a time-stepping simulation where you say, okay, I'll slice time up into little epsilons and simulate this by first having the ball move this far, and then this far, and then this far, and then this far, and this far, and this far, and so on. And there's lots of problems with that. One is, it's a lot of work to go through all of these time steps. You don't just get fast forward to it. And another problem is, actually the time steps are never perfect, so you never really get the exact collision of this other ball. At one point in time, these two balls are not touching each other. You skip this step forward, and now the two balls are actually colliding in the sense that one is actually really hitting each other. So you got to deal with all kinds of boundary cases there. And so it's much simpler, and dealing with those boundary cases is as hard as just figuring out the time that these two things should collide. So it's simpler and usually more accurate depending on how you deal with these things to use priority trees in this way. And those are the two operations you need to make. Every time some new event gets created, you throw it in the queue, and once you're ready to handle the next event, you remove the smallest value from the queue is the event that's going to happen soon. Okay. So there's just a couple of applications so you know why these things are useful. And what we're going to look at first for priority queues is something we already have a pretty good idea of how it works. It's a binary heap. And this is a complete binary tree with the heap model. So remember the heap property, and that is the priority, I know u is bigger than the priority of the parent. The smaller priority should be at the parent between those two nodes. And of course, that means that the smallest priority will have to be at the root because there's no other smaller priority to put at the parent. The root's the only node that doesn't have a parent. And it's a complete binary tree, meaning it looks like this. Every level except the last level completely full. So at level I, there will be 2 to the I nodes, so 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, except the last level. And the last level is filled up as much as possible from left to right. So you won't have some dangling child over here or 2 children over here until you've filled up all the ones to the left. Okay? Now, binary heaps, when they're implemented this way, it turns out that there's a really tiny implementation of them that is almost always the right implementation to use. And this is interesting because it actually uses a technique that goes back I think it's over 500 years. So back into the 1500s, I think, there's a guy named Eitzinger. And he had a really boring job, or he made his living in a really boring way, at least I think it's boring. He maintained big books of family trees, of course, royal families or noble families. Whatever, families of note. are the family trees that you could focus on a person and know their lineage. So these were the things that they start at me, and then you can look up at my mom and my dad, and then 2 levels would be grandmom 1, granddad 1, grandmom 2, granddad 2. And so on. So, 3 levels would be the 8 great-grandparents that you have. And hopefully, when you do this, for a reasonable number of levels, what you see here is a tree. And although it's royal families, it's often not a tree. Sometimes there's some little bit of crossover, but you just pretend it's a complete tree. So he had this, he wanted to make these kinds of books, right, that focused on the current head of state and then showed everything leading up to this, that made up this person. And, well, the problem is, even with this chalkboard, which is a really big thing, much bigger than a book, we're not going to get too many levels out of this before we can't draw this thing, right? The size of the eye level is 2 to the eye, and so this thing is just, it's going to get too wide very quickly. It won't fit on this chalkboard, and definitely it didn't fit on the pages of the books that he was writing. So he wanted a way around this, and so what he really wanted was a method to take a tree, which is this somehow, we think of it as a 2-dimensional structure, the way we draw it all the time, but pack it into 1 dimension. So pack it into a linear structure. So for him, the linear structure was just the lines of a book. He wanted to write these things down 1 line at a time. And we're going to borrow this idea because we also want to do. So the way he did this was he said, okay, I'm going to write down on line 0, I'll write down me, on line 1, mom, 2, dad, 3, grandma 1, 4, grandma 2, dad, 1, 2, dad, 2. So this is 0, 1, 2, 3, 4, 6. Like that. So he actually was doing a breadth-first traversal of his trees. So we'll do the same thing. So, we're going to, the root node of our tree will be stored at position 0 in the way. These will be stored at positions 1, 2, 3, 4, 5, 6, and so on. Okay. So far, so good. Seems like a reasonable thing to do. But I guess one question is, why did he pick breadth first order and not, I don't know, depth first order or one of the tree orders or the post order traversals of this tree? Why breadth first order? Well, think about what you might want to do with this thing. So you might be looking at someone's lineage and you say, okay, I'm studying me, and who is, there's my great-granddad, or my granddad, and well, I might like to know, well, what was this guy's father, or what was this guy's mother? And in a tree picture, that's really easy. You would here, and you just say, okay, here, 2 columns there. But in the book, you got to flip to the right page or jump to the right line number. The nice thing about this breadth first order is, given the line number for this guy, you can know the line number of his 2 children just as an easy calculation. So it's important that these things were numbered, so each one had a number associated with it. Well, let's see if we can figure out what that calculation is. So, suppose we take some node I, and we would like to know, so I means this, I is the number of this node in this picture, and we would like to know what is the formula that gives me the number of i's left child, which will be the position in the array. Yeah? 2i plus 1. So the left child of I is equal to 2i plus 1. 2i plus 1 equals 1. So let's check that out. And 0, so I equals 0, 2i is 0, plus 1 gives me the left child. Let's try that. 3. For I equals 3, 2i is 6, plus 1 gives me the left child. Do it for 4. 4, 2i is 8, plus 1 gives me 9, and that gives me the left child. So the left child is at 2i plus 1. What about the right child? Yep. 2i plus 2. And that's just because these things are numbered in breadth first order. So if 2i plus 1 is the left child, well, the next thing that receives the number is the right sibling of that. 2i plus 2. There's another way of writing that, by the way. I just write that because it's always surprising to me when you guys write things like final exams. I will often have maybe this will be one of the choices in the multiple choice exam, 2i plus 1. And that happens, I'll end up fielding like 20 questions where somebody has written 2i plus 2, and they tell me that this option is not available anywhere in these choices. So be prepared to do a little bit of arithmetic. Okay. So this is the plan. We want to do this. The binary heap is going to be a complete binary tree, or at least we think of it as a complete binary tree. But actually, the way it's implemented is just as an array like this. And we will do these. We'll have these calculations, left of I and right of I, when we want to know the left and right child of a specific node. And what about the parent of I? What's the formula going to be for that? Yep.
I minus 1.
Yeah. So it's something, we know that it's roughly I divided by 2 because the children are at 2i. It's just exactly figuring out what we need to do. But it's actually I minus 1 divided by 2, and then the floor of that, think of this as integer division. So let's check that. Who is the parent of 1? Well, 1 minus 1 is 0, divided by 2 is 0. Who is the parent of 2? So 2 minus 1 is 1, divided by 2 is a half. Let's take the floor and you get 6. And you can check that for, let's try 14. So we get 13 divided by 2 is 6.5, and take the floor, you get 6. That's the formula for these things. Okay? So conceptually, this thing is a binary tree, but in actuality, it's an array. So let's draw one of these things. Value in here, so the smallest value I can do, 3. Okay, so there's an example of one of these things. It's a full binary tree. All levels are full except the bottom one, which is filled from left to right. And when we map it to an array, we get a thing like this. Is it a heap? Yes, these purple things are the keys. And indeed, if you check every key, it's bigger than the priority. Then the priority of every node is bigger than that. That's all you need. Heap. And you see that there's a lot of flexibility here, right? So these things are they're not like binary search trees where if I drew the tree and told you the values, there'd be only one way to put those values in. Here there's lots of ways. Like, you know the smallest value is at the root, but the second smallest value could be in the left or the right child. Either of those things would work. So there's lots of different representations for a heap this way, which is one of the reasons that we treat them as a special case, because because there's a lot of flexibility, you can do things a lot faster. Well, in particular, putting them in an array like this. Okay, so let's see what we want to do. We would like to add values. Let's say we want to add a new value, x, to the heap. So, any suggestions on how we go about doing that? Yeah. Yeah. So we know that, forgetting about what values are stored where, we know what the tree is going to look like after this. It's going to have one more node, and we know where that node has to go because it has to fill in the bottom row here. So it's going to go right there, which is nice in this array picture because that just means it goes after everything else in there. Okay, so eventually there's going to be a new node there. And we're going to put x in there, so let's take, let's choose x equal to 3.5. So, we want to put 3.5. Well, we might as well put it there for now. Now, is that a heap? No? What's wrong with it? Yeah. So 3.5 is smaller than the priority of the parent, which is 7. So what do we do? So that's the only problem with the heap, right? That's the only place where the priorities are mixed up. Yeah? We can't rotate. Rotating would change this into a tree where the 8 goes down here, and then it wouldn't be a full binary tree anymore. Yeah?
Bubble up.
Bubble up. So what does that mean?
So we look at the parent, and then we get the index that we want on, and then we switch those two, and then we add to that node that we switched.
Yeah. Well, okay. So I mean, 3.5 and 7 are in the wrong order, and so 3.5 should move up in the tree above 7. So we just swap these two values. 7 goes down, 3.5 goes up. Seven moves here, 3.5 goes up. In the array, that's just swapping two values in the array. We know which two values to do because 7 was at index 10, 10 minus 1 is 9, divided by 2. Now we know that this edge is okay. Between this parent and this child is okay. We also know that this one is still okay because 3.5 is smaller than 7, so it's definitely smaller than what was down there before. We didn't take this one back. So the only problem that might be left is this edge here is not satisfying the heap property anymore. And indeed, it's not. In this case, 3.5 is smaller than 5, so we just do the same thing here. Swap 3.5, 5. In our array, this. And so we know that this edge is good now, and we know that this edge is still good because 5 is already smaller than 15, so 3.5 is still smaller than 15. The only thing left to check is this edge, and this edge is okay. 3 is smaller than 3.5, so at this point we can stop. Okay. So it's really a simple thing, just you add it to the end of the array, and then you say, so while the value of this thing is smaller than the value of the parent, and this thing is not the root, so change the order, then you swap with the parent. So it's a super simple thing, and this thing just bubbles up into the array, and which conceptually is bubbling up in this binary tree. So now we have a heap again. Okay, so how long does that take? Yeah. So how long that takes is at most the height of the tree. How high is the tree? Height of the tree is at most log n. So this is the height of h, and h is less than log. Because in a tree of, we did this calculation already, but in a tree of height h, in a full tree of height h, you get 2 to the h leaves, and that means that 2 to the h is smaller than or equal to, and in fact in this case it's strictly smaller because it's also did. So here, take the logs on both sides. The height is less than or equal to log n. So the height of the tree is less than or equal to log n, and this bubble up procedure just walks up the tree one level at a time. After log n steps, you will bubble this thing up to the root. So that's how Other operation we want to do, here's a new one, find min. Find the smallest value. How do we do that? Yeah. We, I guess maybe we first check to see if it's empty, in which case there's an error that should happen. But otherwise, we know what the smallest value is at the root. So this actually takes only constant time. And then the last thing we want to do is remove. So remove is supposed to remove the smallest value from the heap. How do we do that? So smallest value is at the root. So we want to remove the root from the heap. That looks difficult. But we have strategies for this deleting difficult nodes. What's our strategy?
You try falling down to and then you get from the last time.
Yes, I can try bubbling down the root. But what does that mean exactly? I mean, what if I bubble down the root and, in fact, in this picture, in the way I see it, well, this is a bad picture, but what if I bubble it down and it ends up down here? And that's still not a node that I'm allowed to delete. It's not leave this thing. Yeah.
Could you swap it with the last value, remove it and then bubble down the
Yeah. Yeah, so we want to get rid of the root value, which we do. We take it out. And we need a replacement. And we know, again, what the tree is going to look like after we're done. It's going to be missing this node here. So we might as well take the replacement from that node. 7 goes up there. And now this node is actually gone from the tree. So that's easy to implement in the array. We take the element at position n-1 and copy it up here. And of course, we decrease the value of n because there's one less element. But now we have some problems with our heap property because we took something that's way down at the bottom level, that's probably pretty big, and we stuck it up at the root. So it's probably not the smallest value in the heap. In fact, it almost never is in that heap, only has 2 levels. So we need to fix that up somehow. So how do we fix that up? Yeah.
Swap it with whichever is a little smaller.
Yeah. So we look at its 2 children, and this gives us 3 different values. The smallest value in the tree will have to be there. Will have to be one of those 3. And so in this case, it's 3.5. So the smallest value goes up, and this one comes down. So 3.5 goes up, 7 goes down. Here we were looking at these 3 values, and we decided to swap them this way. And now we know that this edge is okay because we actually compared 3.5 and 4 and we decided that 3.5 was the winner, so it's okay to be up here. It's smaller than this guy. We know that this edge is okay because actually 3.5 is smaller than the smallest of these 3 values. And so now all that's left are these 2 edges here below 7. So we'll need to fix those. And we just do the same trick again. Compare 7, 15, and 5 to figure out which one is the smallest. In this case, it's 5. So we swap 5, 7. And now we compare 7 and 8 to see which one is the smallest. 7 is the smallest. We get some. Okay. So basically, we are doing a sort of funny thing here where, well, we take this last element and we put it up as a root. And then we find a path in this tree that repeatedly goes to the smaller of the two children. And we use that to insert 7. So if you look at that path, basically, in the picture like this, there's always a path in the tree that goes to the smaller of the two children. And we just stuff this new node 7 up here. And basically, so all of these are getting bigger as you go down, and 7 fits into this sequence somewhere, and that's exactly what we do. So it's like an insertion of 7 into the sequence where we pop these guys past 7 as we realize that they're all smaller. Yeah? The 10th element of the array is left in. Well, so yeah, so the question is, wait a minute, you're using an array, and arrays don't grow or shrink, but actually we've seen tricks to make arrays grow or shrink. One of the first things we saw was how to implement a list, which is something that can grow or shrink arbitrarily as an array. Right, so the trick is every time the number of elements gets to be more than what's in the array, double the size of the array, copy everything over. And we've already analyzed that and seen that that doesn't add much to the overall cost. The add operations and the remove operations each take log n time, and we saw that the cost of growing and shrinking the array only takes constant advertised time per operation. Yeah.
Doesn't that last step nodes 4, 9, 10 with 7, 8?
Well, we're not comparing 10 because it's out of, it's not
just
a
check.
yeah, so you just check amongst the, you take the current node, which is the one that has 7, and amongst the two children. So there's a little bit of cruftiness in the code, which is like, says things like, you know, if the left of I is less than n, then check, you know, right of I is less than n, check. So a little bit of boundary cases to avoid, you know, you can end up down here and then you'll be checking something that's actually pretty far out. Okay. Questions? Good. So that's it. We've proven the theorem about binary heaps. And just to write it down precisely, because it also uses amortization, basically going back to one of the first things we studied, making an array that can grow and shrink. So the theorem is that binary heap implements the priority queue interface. And adding an element ignoring the cost of all to resize. These are things for resizing the array. Adding an element and removing only all of them. That's- So, all the stuff we just talked about only takes a long end time, constant time for finding them in. The stuff that we didn't talk about is what happens when the array gets full, in which case you double its length and copy everything into this new array. And what happens when the array gets less than 1/3 full, in which case you make it twice the size it needs to be and copy everything into this new smaller array. But we've analyzed that before. That's something we did very early on. All that extra copying basically amortizes out to copying 2 values for every value that you insert or remove into this structure. All right. Yeah.
So we can find the max or
Yeah, so finding this is not helpful at all for finding the max. If you want that, then store 2 heaps, one where you reverse the roles of min and max. Then it'll store the maximum value. There's actually other structures that do exist. If you want to keep track of the min and max, there's a thing called a min-max heap, which does a trick of interleaving layers that actually does allow you to find min and max all in one structure, but more easily is just use 2 heaps. Right, that means when you add something, you have to add it to both heaps. When you remove something, well, then you've got to do a bit for it. But we'll see a way of dealing with that soon. Okay, so these heaps actually lead to a really nice sorting algorithm. So typical sorting problem is you're given an array of n values and organize them into sorted. So let's call that non-decreasing order. Well, actually, let's say, let's do it the other way. Let's say in decreasing order. So this means the largest first. So that's typical input to a sorting algorithm. And there's lots of sorting algorithms, and that's because they all have pluses and minuses. But one nice property of a sorting algorithm is that it'd be what's called an in-place algorithm. And that is that I give you this array A, and it's nice if you don't have to then allocate a whole second array to do the sorting to help with the sorting. You can do it all inside of A. That's a good thing. And the reason it's a good thing is, well, allocating a new array is a potential failure point. So if this array, the data that I want you to sort just barely fits into memory, I don't have room for a second array that will store the data. So it's nice if you can sort in place that way. And of course, it's nice if you can sort quickly. So there's a very clever algorithm that uses heaps for this. And here's how it works. So step 1, what's called Heapsort, is we turn A into a heap. So we take A, this array, and we turn it into a heap, a binary heap. Now we know, that we can represent a binary heap in an array like this. We'll see how we can turn an arbitrary array into a heap this way. But that's what we do. now after step one, this thing is a heap. And we want to, because of the way I've stated it here, we want to sort it into decreasing order. So the largest element should be at the front of the array, and the smallest element should be at the end of the array. So right now, if we build a heap, the kind we've been talking about, the smallest value is at the front of the array, in exactly the wrong place. So what should we do then? Yeah? Nope. It's even more clever than that. Yep.
Use your index values.
Nope. So, suppose I delete the smallest value from the heap. Does that free up any space in the heap? In the array? Which space does it free? It frees the last space, here. Now, if I'm sorting into decreasing order, the smallest value, the one that's in my hand that I just deleted from this thing, is supposed to go here. So I put it there. The minimum value goes there. And now, I just pretend that this thing is a heap. Well, it is a heap that stores n minus 1 values. So now if I delete the smallest value, that frees up a spot here, which is exactly where that second smallest value is supposed to go. And I just repeat this. We just call remove n times. Placing the remove element position. Let's say n minus I, where this is the ith time we call it. The first time it goes at position n minus 1, second time at position n minus 2, and so on. It's super easy. Throw it into a heap, and then repeatedly remove the element and move it to the end. Okay. So how long does remove take? Well, it takes only order log n times. We call it n times. So this step of the algorithm takes order n log n times. And we'll see that actually for these kinds of sorting algorithms where you're comparing values, that's the best you can do. You can't do faster than that. But now we need to figure out this step one here, which we haven't quite worked out. How do we turn this thing into a heap? And it turns out, well, there's a few ways to do it, but a guy named Floyd discovered a very clever way, which is, so I'll just erase all the values here. And we'll build a heap, or if we want to build this heap, so-called bottom-up, starting by making sure that the smaller subtrees are heaps, and then working our way up the tree. So we start, for example, at position 10, which is this node here. So the subtree rooted at here is just this tree that has only one node in it. Is that a valid heap? Let's see, it's a complete binary tree, and it certainly has the heap property because there's no edges to violate the heap property. And the same thing at positions 9, 8, 7. These things are all good. 6, 5 is all good. In fact, we don't even have to start worrying until we get to some node that has children, which actually here means we don't have to start worrying until we get into the first half of the array. So this is already a collection of little heaps of size 1, in some cases, of size 1. we need to deal with this guy. So what do we know about this guy? We know that it has 2 children, and they're already both heaps. But the value here might not be the right value. So have we seen that problem before? So where did we encounter this? When we delete, when we remove something, that's exactly what happens, right? We take some value from the end of the array and we stick it up at the root, so it's in the wrong place. But what we have going for us is that the 2 children of that thing, we know that they're perfect heaps, and that allows us to insert this thing in and put it in the right place. Okay. So we just call the same routine that when you call delete, it does this, you just call it on this node. So we call that thing heapify, which fixes a heap as long as the only problem with the heap is the root is in the wrong place. So we just call heapify, heapify, and now we can call heapify here because both the subtrees have already done that. Heapify. So literally, the make heap code is for I equals n over 2 down to 0, we just call heapify the subtree root of that position. The heapify is the thing I showed you we do when we're deleting. We were always doing it at the root, but it can work in any subtree. Okay, and heapify takes O of log n time, and so, right, because it just takes this value and pushes it down in most log n places. So this takes O of log n time. So this whole thing takes O of n log n time because we do it n over 2 times. So both steps, turning it into a heap and removing the elements, can be done in O of n log n time. So the total running time of Heapsort is O of n log n. See, believe that? So here's something else. This is actually an overestimate. This first thing does not take time O of n log n. It's actually faster than that. If we look at what happens, there are n over 2 values for which heapify actually doesn't get called. So how long does it take to not call a function or not do anything? Well, that takes 0 time. So if we add up the cost of all these calls to heapify, we'll end up with n over 2 times 0. That's good so far. We're doing really fast now. And now there will be n over 4 values where the height of the tree is only 1. So let's, the big picture looks like this. There's all the leaves in the tree. There's n over 2 of those. And we don't even call, we don't do anything for those. We actually skip them because we start counting at position n over 2. And now at the next level, so we have n over 4 trees of height 1. And then at the next level, we have n over 8 trees that look like this. So there are n over 8 trees of height 2. So if we add up the cost of heapify, it's 0 times n over 2 plus 1 times n over 4 plus 2 times n over 8 plus 3 times n over 16 plus 2, 4, and so on. Or if you like, you can write this as n over 2 times the sum I equals I over 2 to the 2 times this sum. Yeah?
Could you explain why it's 4 times 2 since we're only comparing the two values just like?
Oh, no. Because it's at the third level, we have 8 over 8 nodes that look like this. So we take this guy and we compare it to these 3 and it moves down, potentially moves down a level, and then we have to compare it again to these 2. So basically it could move all the way down to a leaf, and so the time it takes is the height of the tree, which is the I in this formula here. And this sum, we won't do it, but this sum actually only adds up to a constant. The sum of I over 2 to the I is only a constant. In fact, here I think you end up with something like, don't quote me on this, but something like 2 times n is the total amount of these steps of moving down that you have to do, which means that actually this first stage of the algorithm runs in O of n time. So we can take an array, turn it into a heap in linear time, and then all we do is remove elements from the heap. That's the slower part of the algorithm that takes n log n time. So this is actually a negligible part of the running time. This is the part that